All right, so it looks like our next speaker is Boyuan Chen, who is an assistant professor at Duke in the mechanical engineering and materials science and the electrical and computer engineering departments with research interest in robotics, computer vision, and machine learning.
Awesome. Thank you so much, Erica. Let me share my screen. All right. Can everybody hear me and see my screen?
Yes.
Awesome. All right. Good morning, everyone. This is Boyuan Chen from Duke. And today I want to tell you a little bit about our work on this very big idea of having a robot as a scientist. And this basically involves our efforts on a spectrum of efforts on even automating the robot design efforts by itself as a sort of a representative example of a general purpose electromechanical system automation, but also involves some of our other line of work that try to automate scientific discovery from raw data from the scientific computing community. All right, so the first work I'm going to introduce is built by all the roboticists, right? So all the team members you see here are roboticists that kind of have been trained. One of the courses that developed by Duke involves how we can design a Lego robot from scratch. So there are only two rules in the class. One is that you are given a limited resources, right? You have 8 motors, a Raspberry Pi, a bunch of electronic components you can use, and 3D printer. And the other rule is that no wheels are allowed. You have to build a legged robot. So these are the two only rules I give to the students. And the whole semesters of the class and mostly undergrad students' goal is to go design the robots from A to Z. This is actually a very time-consuming effort. You will know that students have to start from scratch of sketching ideas on the paper and all the way to 3D printing, CAD modeling, 3D printing, manufacturing, assembly, build a simulation, and write gate optimization algorithm, reinforcement learning, training the policy, and back to deploy to the sim to real transfer. And this is eventually what you see as sort of various kinds of aesthetic design with many different morphologies that we have the walking and a dancing competition in front of the Duke Chapel. And this process typically takes a few months. And although all the students can design the robots, but not all the robots, and most of the robots cannot walk as smooth as we can think. And so this is actually a very classic example of if we are designing a new electromechanical system, what is sort of the typical process would be. And this ranges from designing robots all the way to sort of designing tools that we need to use, designing machines that we can use, and anything they can think of like biomedical devices and stuff like that. And this is actually not the first time that we kind of imagine we can speed up this process. So even with domain experts, designing robots could take many, many years. And about 12 years ago, there is a cover on the economics where people imagine about the third industrial revolution with the rising of the 3D printers that we see. A human can sit in front of a computer, designing things or even prompt what they want, and eventually they can generate a robot or machine or even airplane from this. However, 12 years later, we still don't see anything like this existing in the real world. Most of things are still manually done, and it requires years of training for people to get ready on a certain part of the workflow. And you need a team of efforts that develop, it requires several months, even years to develop a working machine. So basically, the first project we did under the FunSci program is aiming to automate this process in a sense that can we leverage the foundation models and having only text prompts from humans and generate the entire physical functioning machine. And the only human efforts there would be the initial prompts in terms of what do you want a robot to look like, for example, is aesthetics, and what performance you want to care. Do you care about more energy usage, or do you care more about optimizing a walking performance, say, tracking a velocity among different directions? So we call this framework as text robots, and essentially has a few steps. The first step is a human simply using a UI interface that choose what they want. For example, you can select, you can type in what you want a robot to look like. For example, it could be a robot that look like a bread, a robot that look like a chimpanzee, a robot that look like a cheetah that has 4 legs. And you are only given, the machines are only given limited resources, and they actually have the same resource that were given to the Robot Studio students. And the other thing that human can select is, what is the sort of the performance metric you want to optimize? Will that be a accurate velocity tracking, or will that be optimizing the energy efficiency? And that is the only human input. After that, the machine will run through a whole component of pipelines that the first step is where we leverage foundation models to accelerate the ideation. And this is where we actually see the most promising direction of foundation models is to offer many different ideas, and especially good ideas that are not built on top of random sort of a combination of basic components. And this is actually the most time-consuming part for human design, where if you look at the past about 2 to 3 decades, automated robot design is actually not a new idea. People have tried to do this, and the way people do that is largely based on evolutionary algorithm, that people come up with basic morphologies, for example, bars and linkages, and they use random search at the beginning to combine them and come up with different solutions. And then we do a filtering on top of that by evaluating solutions, and we evolve the designs over and over. However, the key idea here we're doing is to replace that whole randomized components with a foundation model, and specifically we use text-to-mesh model. However, if you look at the text mesh to mesh model, most of these are given a text prompt and can generate a 3D mesh model. Most of this time are basically for graphics usage. You're going to see people talk about how you can apply this into a game assets. However, they're not grounded into physical functioning machines. So our second step involves our own geometric processing algorithms that basically look at all of these static meshes and think about how we can convert these static meshes into a robot model that have the kinematic chains, and even consider what's really important and basically has never been considered in the design phase is electronics and manufacturability during this phase. So our pipeline also includes the considerations of the electronics and manufacturability and sim-to-real transfer capabilities, all within the second step. And after that, we will perform a inner loop and outer loop optimization, where the outer loop look at the morphology of all the possible ideas proposed by the foundation models, and then we can start our evolutionary algorithm on top of this very fast ideation. And then in the inner loop, we can train a massive parallel reinforcement learning policy in the simulation that can give us a walking policy very fast, while balancing the optimal functions specified by human preferences. And the last step is because we actually consider the electronics and 3D printing manufacturability and sim-to-real transfer already during the design phase, we can easily assemble things. So we reduce the amount of efforts from several months and even several years of efforts into several hours, and sometimes less than a day. You can have a physical walking robot coming out of a 3D printer, and the only input from the human would be the initial prompt design. So this is sort of what it looks like when you have a static mesh. We basically slice over different dimensions to figure out the cross-sectional area analysis to figure out where are the best motor placement as the initial hypothesis to ground the static meshes into a kinematic chain of a robot. And after that, you're going to see we can easily 3D print the parts we design. And because of the way we consider electronics, we have a pre-built motor boxes that applies to a general purpose robots. We can take about less than 10 minutes to simply snap things in and build a functional robot. And during the inner loop of reinforcement learning, you can have many sort of objective functions you can optimize for. For example, if you care about linear velocity tracking in the domain, or you care about the energy cost in the battery, you can put more and more objective functions into this loop. And because of we're running on these very fast, GPU parallelized simulations, we can quickly generate the walking policies and iterate things really fast. So this is sort of the optimization loop look like. You start with initial population. You start with, then the inner loop will be the RL training, where the outer loop swap different body components or changing the orientation of the axis of the motors, or you can extend and shorten the length of each of the links of the robot body. You can do many different things on top of that. But this really gives us a very good jump start. So easily you can generate many of these ideas simply by changing one word in your prompt. For example, what do you want the robot to look like? You can specify it as ant, bug, dog, cheetah, Brad, whatever you want to name it. And after that, this is sort of the main takeaway message figure, where if you look at what we're showing here, the previous state of the art is a framework called a RoboGrammar. So essentially, it is a tree structure that specify a grammar for combining different basic components of a robot design. However, if you start with that, most of the time at the beginning, you're going to actually waste on figuring out what is the good randomized initial configuration. And it turns out most of these robots start with random, even with a good representation of the grammar, still gives you very low reward. So what I'm showing here is without training or without any optimization, the initial performance of these robots, when we try to ask them to train a reinforcement learning policy for them to walk. And if the exact same environment, exact same code, the only difference is that our text to robot initializations are proposed by the foundation models. And you can see there's about a 400 to 500 times improvements on the initial performance without any optimization. And this is very different in the sense that if you look at almost all the evolutionary design curves, you're going to see the curve starts very low and it gradually improve, right? So this is also one of the major bottleneck of evolutionary algorithm is that typically it's very slow. However, in our case, our initial idea from the foundation model, because it has the baked-in prior knowledge of animals and biology, we can actually generate much more realistic robot designs that already have a much higher performance as a jump start. And what's really interesting to us is that if you train your robot based on a specific bank, for example, all of your robots generated are from these robots that look like a bug or look like a dog, then you are going to have improvements on the performance. And pay attention that we actually start from a very high reward, and the improvements are actually not that large after the optimization. So even initial one, you have very limited time to generate some robots that you require very fast and very cheap. The whole robot costs a few $100s. You can actually do the initial initialization and it can work really well. However, when you try to increase the diversity of the bank, for example, what we do here on the purple curve is to combine all the 3 banks of the robot and then do a joint optimization when you have more and more diverse prompts adding in there. You can see that there is a better scaling law in a sense that with more diverse species, you can have a stronger performance of the robot. And this is really exciting in the sense that the only thing that a human needs to do here is to simply increase the diversity of the bank, other than really try to figure out how do I think about adding diversity in the robot sense, and how do I hire a roboticist can actually come up with more diverse and a creative idea. So you simply just come up with new words in a language and simply prompt the models multiple times. And this takes a few seconds, then you can generate a much more higher performing robots. So these are some videos that you can see even at the beginning, right? So this is 0 shots. There is no optimization on the body. The robots can already work pretty well. And when we move closer and closer to higher up on the reward, you can see the robot start to make more sense, that it has a better sense of usage of the joints of the robots and having different kind of interesting morphology come out of this. And here is sort of what the real robots look like when we try to print it out and for the first time directly deploy that to the real physical world. And this is where we kind of try to optimize the velocity tracking on the forward velocity. And this is what you see a robot behavior that is optimized for energy efficiency. What's interesting is that robots that typically optimize for energy efficiency typically has lower base and shorter body that has lower mass property of the body. Where if the robot is optimized for velocity tracking, it typically has a longer leg and has a wider body, so that it actually has more space and to take a larger step. Another example we can see here is after the robot is trained, because one of the objectives the human users specified was to track velocities, you can use your keyboard to control the robot, steady operate it, and move around in the 3D space. Again, all of these were built in less than a day, and the only human input would be how you can, what do you want a robot to look like, and all of the joints are actually figured out by the machine itself. So this is very exciting, especially if you look at the knee joint and the shoulder joint, where the robot can actually leverage this to know how to turn and respond to different velocity tracking commands from different directions. And we also further look into how do we actually refine specific parts of the robots. So one thing we did was, what if we simply change the robot design by having a different set of environments? As we know, animals would evolve into different morphology and in different sort of walking policies when they are facing different environments. So we generate many different curriculum to train the robots on having a rough terrain with different complexities. And you can see that the general robots and velocity tracking robots have similar foot design, and even though they have slightly different body configuration. But when you try to train the robots on a rough terrain, the foot actually turns out it needs to be some sort of a round shape. And when we observe the walking policy of these kind of robots, you will see that the robots that look more like this sort of two-finger feet, you will see they typically will get stuck on the complex terrains. It's these rough terrains where a round feet actually fit better into this complex terrain. So you can see all kinds of interesting improvements, even by changing environment, how robots design can respond to it. But again, when you need to make such changes to a robot, you need the domain experts to take lots of efforts to make such changes when the environment is different. However, in our case, this is simply one command line. You would switch the environment, you deploy the system, and suddenly you will have what you want on the optimization of the robots. And another line of work I want to discuss is, the first one, we see the potential of having the foundation models to do fast ideation. Of course, we're actually keep developing our method on that to improve the robot design. Another line of work we are looking at is how do we find what are the important inductive biases we actually need to have when we design very robust and automated scientific workflow to discover novel knowledge from data that we have no knowledge about. Right, so let me give you a quick example. If you are familiar with mechanics, this is probably Mechanics 101 textbook example. You have a single pendulum. And what you typically do is the textbook is going to tell you, okay, let's perform a force field analysis on the system. So you're going to draw an angle, and you're going to say, okay, the derivative of the angle would be angular velocity. And with all these two variables defined, you can, based on f equals ma, you can write down the dynamical equations as I'm showing here. And we're done, right? But here are a few things that I feel has been ignored for a very long time. If you ask neural network, what are these the variables that actually you're using to describe the same system? If you train the model that do the same thing as human, we try to train a model that predict the future of the evolution of the system. The AI system is going to tell you a variable that looks like this. And if you try to run it again, it's going to tell you like this. In fact, this is true even in dynamical system theory, where there are, in theory, many, if not infinite number of possible ways to define even that single pendulum system. It is not always just going to be theta and theta dots. There are many, many ways we can describe the system. The magic is we always have to make sure there are two variables. It always has to be two variables to have a minimum description of the system. And these are the things we call the state variables, right? And what we have seen right now are state variables are given to us. We know what to measure. We know what are these variables we can use to write down equations. However, how about this system, right? There are vast amount of systems that we simply do not have enough knowledge about. And if you look at a fire system, and this is a real fire system, we don't know what are the angular velocity of the system. And I think this is also the big barrier for us to really pursue scientific discovery on many complex systems where we have such a huge amount of data recording from that, but we simply don't know how to interpret the data. And one of the major bottleneck is we don't even know what variables we need to work on. What are the variables we actually can look into? And how do we, if we don't know the variables, how do we write the equations? And how do we even predict the future of the system? So the first inductive biases I want to talk about here is the dimensionality. So first of all, before we even know the variables, we want to figure out what is the lowest possible dimension we can work on the system so that we can even perhaps derive variables from that and further down writing the equations for that. So our goal is looking at a video. So the only input we are requiring is a video sequence. And how can we look at a video? First of all, figure out what is the lowest possible dimensionality that we need to describe the system. And second, what this dimension actually give us the variables are. Are they the same theta and theta dot as we described before, or is it something else? And I think this also will help us on understanding and answering some of the very big questions, which is how do we derive the variables, and how do we make sure we can generate video predictions? Even you see all this very amazing work from OpenAI on Sora models that can generate future videos, but does not follow physics, where you can see objects suddenly pops up, objects suddenly disappear, and this is actually not a new phenomenon. We actually know this on video prediction models for many years. So to answer that, our first work was published about 2 years ago on the cover of Nature Computational Science to answer this first question of what is the right dimensionality to work on and what are the variables we need to work on. And what I'm showing here is our method could successfully figure out what is the estimated dimensionality, and typically what we call the intrinsic dimension of the system. And if we operate our future video predictions on this particular dimensionality, the right side of each pair will show the video predictions from our framework, which also is always robust, stable, and give you accurate physics prediction. Well, on the left side is the state-of-the-art video prediction model. You simply train, as you're training a language model, predict the next word, and now you predict the next frame. You will see that at the beginning, the first few frames are still okay, but when you roll out this even less than a second, the whole video becomes blurry, plain background, and you see objects start to distort, right? And if you watch the video generation domain, you will know this is not some news that you actually see this all the time. So having the right dimensionality and figuring out the meaning behind them is really critical. That at least will help us generate videos, and then understand the systems. For example, we can rank the complexity of the systems, and then we can do the same for the fire system as well. And the real reason behind this is, according to computational physics, if you're not constraining the latent space to have the exact lowest possible dimension to describe the system, if you make a tiny little mistake during the autoregressive prediction, it will have a very large chance to go out of the true manifold of the system. However, if you're constraining all the prediction that has to go through this smallest bottleneck possible, it will always be constrained on this manifold. So even though you have small mistakes, it can be automatically corrected in the sense of constrained manifold space. The second sort of idea I want to talk about is dimensionality not only matters, but for the variables you discovered, but also for the equations you try to discover. So it's well known as a Koopman theory, where people try to find out how to explain highly nonlinear dynamical systems is to try to find the linearized form of the system in the latent space. However, the Koopman theory also tells us that if you want to do that, what you need to do is to expand the latent dimension to be much higher than what you have. And in theory, this has to be infinite high dimension. So this was impossible. And we found actually through a proper training scheme and considering the dimensionality and the mutual information of the system, what you can find is actually you can even sometimes with the same dimension as your nonlinear dynamical systems and even reduce the dimension of the system, you can still find very effective linearized systems. So this is in contrast of the Koopman theory that I've seen before. And with that, you can do long-term predictions as we're showing here. You can discover the invariant sets of the systems from very complex nonlinear dynamics. And this is one of the sort of Nobel Prize winner discovered neuroscience model that we can, for the first time, actually show there is empirical Lyapunov analysis we can do to show the stability of the system. And all of this knowledge can be discovered by having a reduced dimension on the linearized form of the system. The last one I want to talk about, the inductive bias, in addition to the dimension of the variable and dimension of the latent space to figure out the linearized equations, is to look at the variables we discovered in the first place. So all of these variables I'm showing here are projections onto two-dimensional space, where the variables are discovered by the machine learning models. They have the same dimension, as we say, and they can accurately predict the long-term future predictions. However, here is one catch. If we want to write down the equations of the system, all of the equations that we have for now things like ordinary differential equations or partial differential equations all require the variables are continuous. Now, if you visualize them in a time domain, you can see that these variables is discontinued. You can see colors jump here and there, and you never actually see the variables have a continuous stream that form a temporal trajectory of the system. So from this, you cannot derive any equations. They will be scattered points here and there. They can make the predictions, but we don't understand how this can be connected with human physical language to speak about physics. So our efforts on that, on the last one, is to think about how do we enforce continuity on the latent space of the variables. What I'm showing here are a range of systems that go from simple spring mass system to single pendulum, chaotic double pendulum, to a cylindrical flow data set on study the turbulent flow. And what you can see is that the second row I'm showing are the variables we discovered by enforcing continuous and a dimensionality constraint automatically discovered. These are V1, V2 that does not have the exact same physical meaning as human-defined variables, but they show up the same pattern. And you can see even on the most challenging turbulent flow data set, all of the data set variables basically start to follow a repetitive pattern that form the periodic pattern that also corresponds to the true physics of the system. The last row are also the gradient field you can discover from all of this. And if you have the gradient field, you can essentially connect this with all the knowledge we know about how to interpret and study the nonlinear dynamical systems in the traditional textbook. So this is very exciting to us. You can do many things with that. You can see at the top row, these are automatically discovered invariants, the equilibrium system states of the system. So one thing that is really interesting is none of these equilibrium states were in the original data set. These were generated in equilibrium states, and these are actually videos that you will see double pendulum. The discovered equilibrium points will be, they actually stay static, but none of our data actually shows that these are static. You can discover the natural frequency of the system. So the omega hat are the ones we discovered as the variable, and the omega is the true natural frequency of the system. Again, all of the knowledge are input as the video frame. So there is no physical knowledge, prior knowledge we know. There's no measurement of the variables. The only thing we're given is the video. And you can do other cool things. For example, you can generate videos that fulfill physical constraints. You can add a damping into the system with the gradient field. You can observe the chaotic behavior of the system. For example, A and B rows are basically periodic equations. So you can see the discovered variables, even though they start from similar, very small perturbations, they always converge to similar states, where the second and the third and the fourth row, you can see that the systems are chaotic in nature property. We can also discover that by applying small perturbations on the local system, and you can observe the system quickly diverge into different things. So these are another knowledge we can discover from that, and there is a range of that. So overall, I showed the first work that we discussed on sort of the dimensionality. The second and the third one are still ongoing work that we're trying to release something on arXiv in about 1 or 2 months, but I want to give you a sense of the method we're developing in the lab. And with that, I would love to take any questions. Thank you.
Thanks, Boyuan. That was amazing. The second part, really incredible work.
Thank you.
We're running a little behind schedule, so we'll follow up with questions offline afterwards. But yeah, really amazing work.
Thank you. Thanks, everyone.